And we're moving to the last talk of this session. It's given by Jürg Luterbacher from the University of Gießen, and it's dealing with European climate dynamics.
Good morning, everybody. Thanks very much for the invitation, coming here to Corvallis and talk a bit about European climate dynamics. And I want to thank also the co-authors. There are many more which contributed to this research. The outline, after short introduction, I want to shortly present to you the proxy data and the instrumental information that we have to reconstruct seasonal temperature reconstructions for Europe. In the second part of the talk, then I will come to the time series to merge all this information in order to get a representation of winter temperature over Europe covering the last couple of centuries. I will show you some uncertainties related to these reconstructions, trends related, and also how exceptional the current warmth is in terms of the past 5 centuries. Then another point is we know from IPCC detection attribution studies which have been done at Northern Hemisphere annual timescale, and I want to show you first preliminary results, the contribution of natural external factors and human activities on European temperature over the last couple of centuries. And then the last point will be, we know rather well the climate history of Europe for the last 500 years in terms of temperature, but I will show you also the uncertainties we have, and there will be improvements in getting more reliable information. But there's also some new evidence about extending these temperature records for a couple of areas back to the year 1000, and I will show you some examples how they are also related to volcanic events. At the end, some conclusions. That's the well-known Northern Hemisphere temperature variation curve back to the year 200 and we know all these curves from Mike Mann and collaborators. There are different reconstructions put together which cover the last 500 to about approximately 800 years. And that's a very interesting graph taking into consideration different proxies, different reconstruction methods, and they give us also information about temperature variations over the last about 1800 years. The thing here is okay, we can't say anything about spatial representativity, and also Europe is somehow covered in this Northern Hemisphere estimate, and also something about seasonality. So what our aim is to focus on Europe, to resolve seasonal reconstruction, and say also something about temperature change in space, rather than just the mean. So what we are using is we have a compilation of long instrumental series that's quite good coverage, but all these instrumental data, they go back 150 years, 200 years, and some instrumental series go back like Central European temperature back to the mid-17th century. We have a couple of long series also from Scandinavia and Italy. So this is a very nice data cover of instrumental data, but this declines back in time. Before about 1750, we included also a couple of multi-proxies from tree rings for summer reconstructions, documentary information for summer and winter reconstructions, some ice information from the north, and so this looks just a combination of documentary information and natural proxies together with instrumental data in order to get a 500-year time series, and we apply some statistical multivariate regression analysis in order to get information about European temperature variability over the continent back to 1500. And that's how it looks like. The x-axis is time. That's the temperature anomaly with respect to the last 30 years. In black are the single reconstructions for each winter back to 1500. That's the average over the continental area. And from 1901 to 2008, 2009 is the instrumental data from the Climatic Research Unit, and before 1900 is the reconstructions using the different proxies. So what we see if we filter the data, this is the red curve, we see that temperature over Europe in winter times was mostly below the 20th century or the late 20th century, and we see the strong increase in temperature, and mainly peaking at the end of the 20th century and the beginning of the 21st century. And if we take into consideration the uncertainties, these are just the uncertainties of unresolved variance in the calibration period within the instrumental period, and filter them. This is given in these blue curves. So if we go further back in time, the less information we have, the bigger are the uncertainties, also reflected in these error bars. If we consider single winters rather than filtered, we can say about the year 1500 the uncertainty will be plus minus 1.5 degree at continental scale. So actually, if we consider the current warms and also consider the uncertainties just based on the unresolved calibration period, we see that it's very likely that the red curve here is exceptional in terms of the last 500 years. So at the European scale, for winter, it seems that the current winters or the past 30, 40 years seems to be unprecedented in the terms of the last 500 years. Now we can have a look at just multi-decadal periods of very cold winters and very warm winters. And here the very cold winters, if you just take 30 years in a row or 30 winters in a row, then we find the coldest departure in the so-called late Maunder Minimum at the end of the 17th century, and this is about 1.2 degree averaged cooling compared to the current warms. And if we take into consideration the warmest period, these are just the last 30 winters, and they are about 1.2 degree above the average. So at multi-decadal time scale, at European continental scale, the multi-decadal differences point about to 2.5 degrees. Now we want to have a look how they present these mean departures in space. So what we did is we just took these 30 years, we averaged them together and subtracted a period 1931 to 60, and you see the strongest departures the strong departures have been found here over Central and Northeastern Europe, whereas in the Mediterranean they didn't really contribute to these really cold conditions during the Maunder Minimum. In contours, we see some kind of error measures how well we do the reconstruction at this time in terms of validation criteria. So actually here in the Mediterranean, the skill is rather low because we don't have so many data and teleconnections do not seem to work very well. But here in our large parts where we have the strongest cooling, we have also some evidence that our reconstructions have some skill. If we go to the warmest periods in terms of spatial representativity, we see also here that Central and Eastern and Northeastern Europe mostly contribute to these very warm conditions, whereas the Mediterranean seem to be around zero. And we can put also the average between the very warm period minus the very cool period, and we find that the strong departures are found in the northeast of Europe, and the contribution of the Mediterranean is quite low. Now we can ask ourselves, what is the role of different forcings in terms of these temperature changes over the last 500 years? And what we did here is, in black is the annual temperature 15-year filtered. In blue, it's an energy balance model, and in green, and in blue, it's multi-model mean. We took the 3 paleo models and averaged them together. So we see that in some periods we can quite do a good job representing the observations based on this average of the 3 models. And then we can ask, what is the contribution from the different forcing, greenhouse gas and aerosol, solar and volcanic over the last 500 years. That's given here. And what we see that in green here, the solar, at this time scales about 15 years, they do not have such a big contribution in explained temperature in Europe. Whereas volcanic events, you see these peaks going down, so strong volcanic events leading to a cooling. This is annual time scale. I will show you some evidence about seasonal time scale. And what is very evident is here this CO2, which comes out, which is the most significant contributor to the current warm conditions. So actually we can account about 30% of these changes with external variations. Now we can have a look at the super epoch analysis to see for the largest 15 tropical volcanic eruptions in the model and in the reconstructions. Top is the summer conditions in the reconstructions. So after 1, 2, and 3 years after major tropical volcanoes, we find in our reconstructions a cooling. Mostly significant here in Central and also in Northeastern Europe. If we take the multi-model, there's quite a good fit. The amplitude is a bit different, but the overall patterns show by the model is also a decrease in summer temperature, 1 or 2 or 3 years after the event. If we go to winter, that's a completely different story. So what is happening is it brings stronger westerlies, positive NAO, after large tropical volcanoes 1 to 3 years after the event. So we find in winter, in the reconstruction, strong warming over large parts over Central and East and Northern Europe, whereas some cooling here in the Mediterranean. And the models, if you take the average of these three, they point quite to a similar spatial structure. They can also provide this warming here in the north and cooling in the south. The question is now, this little ice tape events or this cooling in Europe over the past couple of 100 years, what is the role of volcanic events? And actually that's what we found in the reconstructions. If we have periods like in the Maunder Minimum, the Dalton Minimum, or around 1600, where we had a couple of strong tropical volcanoes, then we composite these periods, then we find in the reconstruction actually a cooling. A significant cooling. So single events lead to warming, but if you have a composite of a couple of tropical volcanoes within a short time period, this leads actually in winter to a cooling. So this might contribute to some extent to the cooling we found in parts of the Little Ice Age. And this one is also very nicely given in the models. Now we can also ask about the role of solar at these time scales. And actually what we did is we regressed the reconstruction on the EBM output of solar. And this is just the role of solar variability in space in Europe for winter at decadal timescales. And we find actually only small departure, or small anomalies in the reconstructions. And also in the multi-model shows a different response. And actually statistics says that the influence of solar variability at these time scales in winter is very low and not significant. Now we go a bit further back in time. So this was just analysis of the last 500 years, and there's now different efforts to go for regional or even continental reconstructions at seasonal timescales back for the year 1000. And here is a small compilation of Western and Central European winter temperature for the last millennium. Some cover the last 500 years, but there's now some evidence to put them back to 1000. This is a new information from documentary evidence from Christian Pfister and his colleagues. So really information from different diaries, and people can interpret them and can put them, it was very warm or very cold in terms of the 20th century. There is some evidence from Germany as well, some tree-ring information, and also documentary evidence from the Low Countries. So, I mean, this is quite difficult to find here some homogeneous areas. For instance, okay, in the 16th century, most of the proxies, they point to negative set values, so maybe rather cool conditions, but in the past it's quite not so homogeneous actually. And I wouldn't say that based on these reconstructions here, we point also to cool condition in Western and Central Europe, that this is not a reflection of a continuous positive phase of the NAO. The picture is much more complicated, and I think we have to resolve these issues later on. But just one example, if we concentrate on the very warm 13th century, to give you a flavor, if it's just one time series and look in details, then we find this is the 13th century in temperature in Central and Western Europe. And actually, it's a very warm century if we filter everything, but if we zoom within this 13th century, we find a lot of cold events here, but also at the end of this century. So in our respect, this cannot be explained by all the time positive NAO phases. We can do exactly the same for summer. There's some evidence about summer back to the year 1000, and we have to work on other aspects and other time series as well. And if we concentrate again on this 13th century, which was a very warm period in large parts of Europe, we can focus again or zoom in again in this 13th century. And these are indices based on documentary information as well. This is time, this is information derived indices, and the zero value would mean normal condition in terms of mid-20th century, and everything positive is very warm. So we see large parts of this 13th century in summer temperature was really above normal, what we experience in the mid of the 20th century. Nevertheless, there are repeated so-called years without the summer. And very interestingly, here with this V are giving the volcanic eruptions which are known. So what I showed you before, that this strong summer cooling of the tropical volcanoes, we can also find here. And one of a very interesting, maybe one of the strongest volcanic event in the past was in the year 1257. And if we have a look at the perception of the cold and rainy summer of 1258, just 1 year afterwards, we see the evidence Christian Pfister and his colleagues have been gathered for this event. You see large areas where it was very cold, reports from different areas from Central and Eastern, Central and Western European areas, but you don't find anything in the East. And people say, for instance, in England, continuous northerly winds and rain from April to June, famine, high number of bodies with swollen bellies. These are some information that has been gathered just 1 year after this strong tropical volcano, which might be one of the largest over the last centuries or even millennia. And if we just plot maybe an analogous case to this, we find 1860, the year without the summer, after Tambora, where we have strong negative temperature anomaly over large parts of Central and Northern Europe, but hardly any evidence in the West. So we come to the conclusions. We find that the pre-century European winters were colder than most recent decades. The last decades, they are very likely the warmest within the context of the last half of the last 500 years, and the coldest period within this Maunder Minimum period. And paleoclimate models, they are important, of course, to explain these changes we have found, also this data model comparison, which is very important. Then we find the detectable influence of volcanoes and greenhouse gases, but the sun seems to play a minor role, at least at these time scales. If you filter 30 or 50 years, that may be more important for a solar influence. The contribution of external factors is about 30%. We have strong tropical volcanoes that lead to European summer cooling, but winter warming. But if you have a period of very heavy tropical volcanoes, this can lead actually to a net cooling also in wintertime, which might be responsible for parts of the cooling within the Little Ice Age in Europe. And we find, or on the way, are some regional continental seasonal temporary constructions which go back to the year 1000. And we find that if you compare these evidence that there is a heterogeneous pattern of cold and warm periods across Europe, and the final statement is we still have large uncertainties in the different areas, in the different seasonality, and the reconstructions I didn't show you for precipitation, so there's still a need for more suitable proxies. Thanks very much for your attention.
Thank you very much, Jürg, for this very interesting walk through 500 to 1,000 years European climate. We have time again for 1 or 2 questions, please.
Yes, for the volcanic influence when clusters of volcanoes lead to cooling in the winter rather than warming, why process? Is that sea surface temperature from heat storage, or is it some other process?
It's a good question. Actually, we just made the comparison, and actually I can't answer you for the moment, but maybe Casper has an answer on this at continental scale. From the model point of view?
Yeah, there is definitely some memory in the ocean, but in this area, what we have found in simulations is that the sea ice expansion that is a bit delayed is probably the strongest message into this memory that can extend. However, if I already have the microphone, I would like to comment on this distinction between periods where there are substantial groups of volcanic eruptions, and you have listed as one of them the early 1600s, for example, where I'm not so sure if that is really a period that would show up as a very unusual volcanically perturbed period. There's one big eruption in there, but it's not necessarily, a big cluster. There are other candidates as well. So I would love to go through your reconstructions and start to play a little bit in which of the groups we would see a continuous cooling and where it might be also some internal variability that masks, this cooling versus warming a little bit.